Hello, everyone. What do I want to do next? And before I dive into Hilbert spaces, is talk about the completion of a normed vector space. So most of the results in this course will require that we have a complete normed vector space or a complete normed vector space with an inner product, which is what a Hilbert space is. So the question arises, well, what do you do when you have a normed vector space that's not complete? And the answer is all normed vector spaces essentially live in a unique Banach space called the completion. Talk about that in a moment. So before I do anything, I want to mention following very easy homework assignment, which is if I have a normed vector space and a sequence xn in my normed vector space converging to x, then we also have convergence of norms. In the sense that if xn converges to x, then a norm of xn converges to the norm of x. Right? And we'll use this throughout the course. Right. Okay, so it's not hard to come up with examples of normed vector spaces that are not complete. The kind of trivial example, of course, is just irrationals with the usual absolute value norm. So I claim that this is not complete. Right, and there's really not much to this. Let's say I have a sequence xn that are rational, that converges to an irrational number, well, then this is obviously Cauchy, but this limit does not exist in irrationals because it converges to an irrational number. Okay. Right, so another example, a much more interesting example that naturally leads to, or maybe an extension of this example I'm going to do, naturally leads to the concept of a Sobolev space and a weak derivative, which you'll explore in the homework, is the following. So let's say I have continuous functions on -1 to 1, and let's give this the LP norm on -1 to 1. So in the homework, you'll look at continuous functions that have a first derivative that's continuous on -1 to 1 with the same norm. Or maybe I'll do 0 to 1. It doesn't matter, actually. I'll stick to -1 to 1. Okay. Okay. Oops. I mean on. So here, let's say, to make this a norm, we need p between 1 and infinity. I don't want to look at p equals infinity, particularly because that is a complete normed vector space when you give this the L infinity norm. Okay, yeah, so this is not complete. And we have to work a little harder to show this, but not much harder. Okay, so why is this true? Well, let's just write down a Cauchy sequence that doesn't converge to a continuous function in the LP norm. Right, so let's say this is going to be minus 1. If t is between minus 1 and minus 1 over n, let's say it's 1. If t is between 1 over n and 1, and let's say it's the line segment, or the line connecting minus 1 and 1, for the rest of the t's between minus 1 and 1. So in particular, t's between minus 1 over n and 1 over n. Okay, so you'll notice that in particular, when t is minus 1 over n, both of these give you minus 1, and when t is 1 over n, both of these give you 1. So this is certainly continuous. It's continuous at minus 1 over n and 1 over n, so no issue there. So let me just draw a picture if there's any doubts as to what's going on. Not that there should be, but so let's say here is minus 1. Let's say here is 1, minus 1, 1. Let's say here is 1 over n. And let's say here is minus 1 over n. Okay, so, right, this function is minus 1 from minus 1 to minus 1 over n. It's 1 from 1 over n to 1. And then we just, it's just a line connecting minus 1 to 1 between minus 1 over n and 1 over n. So it should be a line here, but make it a little better. But you get the point. It's a little better. Okay, so right, so Fn converges to big F pointwise, where big F of t pointwise on minus 1 to 1 where this is going to be the following. Well, I mean, it's pretty obvious what this is going to be. You just have to be a tiny bit careful at t equals 0. Well, I mean, just pick, let's say we have a t here. Right, so let's say this is, so this is t, Fn of t. So you can obviously see no matter where t is, as long as it's bigger than 1, then Fn of t is going to converge to, so maybe I'll just put a t here. Right, so big F of t is going to be 1 if t is between 0 and 1. Well, obviously, if t equals 0, no matter what n is, we get 0. And same kind of thing here. You can just stick a t between -1 and 1. So it's going to be -1 if, running out of room here. Right, if -1 is less than or equal to t is less than 0. Right. So by an easy dominated convergence theorem argument, basically there's nothing to argue. Every Fn is pointwise bounded by 1 in absolute value. So is big F. So this here, Fn of t, and raised to the p, this is going to be 0. Right, so that means Fn but this is obviously not continuous. But this is certainly Cauchy because it's convergent to something, to this big F. But this is certainly Cauchy in LP. So in other words, we have a Cauchy sequence of continuous functions that converges in this LP norm to something not continuous. So, right, that proves that this normed vector space right here is not complete. Okay, so let's get to the completion. So the completion of a normed vector space X. Okay, right. So what we're going to do is basically we're going to prove that every normed vector space essentially lives in a larger, possibly larger, complete normed vector space. So how do we build this larger normed vector space? As we'll see, it's not much larger because essentially X is going to be dense in this larger complete normed vector space. So yeah, so X is almost, in some sense, all of this larger complete normed vector space. Okay, so how do we construct this larger normed vector space? Let's say we have two Cauchy sequences. So let's say these are Cauchy. Sorry about that. So let's say they're Cauchy in big X. So we're going to define an equivalence relation on the collection of Cauchy sequences. And in particular, we're going to say this Cauchy sequence is equivalent to this other Cauchy sequence if in the limit they're kind of the same sequence. What the hell do I mean by that? Well, if this limit equals 0. Okay. Right. So basically, xn and yn they're basically the same sequence for large enough n, more or less. All right. Okay. So yeah, my bigger, my possibly bigger normed vector space is going to be the following, and I'll explain why, in some sense, we can say this is, you know, bigger than X. Okay, so yeah, define it to be all these equivalence classes generated by all Cauchy sequences generated by all these Cauchy sequences in X. And just to make my life a little easier, I'm going to call this class X hat. So define this class of Cauchy sequences to be X hat, for lack of anything better to call it. Right, so we have to give everything in X star and norm. So for Xn, defined as this equivalence class of Cauchy sequences, well, let's define the following norm. Well, it's just going to be Xn. The limit as n goes to infinity of Xn. Right, so this is the norm we're going to define on this new, well, it's going to be a vector space. I'll explain, just like before, you basically have a very canonical, very natural addition and scalar multiplication, but I'll explain that in a second. But again, this is the norm. This is how we're defining the norm. Well, there's the question of why does this necessarily exist? And that's a good question. Well, let's just see why this exists. Literally, why does this limit exist as a non-negative number? Well, that's easy. Particularly by the reverse triangle inequality, we have the following here. That implies that this sequence of non-negative numbers is Cauchy. And obviously that means it converges. Because this is a Cauchy sequence of non-negative numbers, it converges to a non-negative number. So this limit exists. So I'll have you prove in homework that this is independent of the representative chosen from this class. In particular, if yn is equivalent to xn, then this gives me the same limit. In particular, lim xn in norm equals lim yn in norm. So this is independent of the Cauchy sequence chosen from this equivalence class. Otherwise, this doesn't make sense. Okay, right. So just to remind you, just like last time, or maybe not remind you, but just like last time, you have an obvious addition. And instead of using x hat, y hat, I'll just literally write, with the brackets and everything. Well, you define this to be, well, if you add two Cauchy sequences up, you get a Cauchy sequence. So this is a Cauchy sequence xn plus yn, the sequence. So it's just a class generated by this Cauchy sequence. And again, this addition is independent of the representatives chosen from these two classes. If xn is equivalent to xn prime, yn is equivalent to yn prime, then the class generated by xn plus yn is the class generated by xn prime plus yn prime. I'll leave that for homework, that this is well defined. And, well, scalar multiplication. It's just really the obvious thing. Well, obviously, alpha xn is a Cauchy sequence. So, yeah. Okay. Yeah, and not that there should be any confusion, but the zero element is kind of the obvious thing. Just take the constant sequence 0, 0, 0, 0, 0, 0, take the class generated by that. So for example, if there's any confusion, something like, yeah, so let's take x's rationals. Then this is certainly a Cauchy sequence. This is certainly a Cauchy sequence in the rationals. So the zero element in my x star here is also given by the class generated by 1 over n. And that's just because, well, pretty trivially, this is 0. So 1 over n is equivalent to the class generated by, or rather 1 over n, the sequence here, maybe I should put brackets here. Sorry, silly, I have brackets. Sorry about that, a little brain fart there. Right, so this Cauchy sequence here is equivalent to the constant sequence, just zeros, just by definition. And I should mention, actually, if you've ever seen the construction of the real numbers, what I'm doing here is probably the simplest way to define the real numbers. Usually you just kind of take for granted that there exists this nice vector space called the real numbers. But if you've ever actually questioned, well, how the hell do you define the real numbers? This is how you do it. There really isn't a simpler way to do it than this. So, right, we are basically defining the real numbers as the completion of the rationals. Okay, anyway, so, yeah, the rest of showing that X star is a normed vector space is for homework. It's pretty easy homework. Okay, so let me prove a few claims here. So first of all, I want to prove that as a matter of practicality, big X kind of lives nice and comfortably inside of X star. What do I mean by that? Well, let's say X is in big X. And let's define a map from big X to big X star, in the following way. We just take the constant sequence X, so it's just X, 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 keep going, and define the class generated by X. So this is a map, perfectly fine map from X to X star. Then I claim that this is isometric. In particular, it's norm preserving. Okay. And also it's linear, so it preserves addition and scalar multiplication. Okay. So what does this mean? So it says that X as a normed vector space, or as a vector space, it's isometrically isomorphic in the sense of vector spaces to a subspace. This is linear, so this is linear subspace of X star. So in other words, we often write that if this happens, X is embedded in X star as a matter, because what this means as a matter of practicality, what I'm putting in red, what this means as a matter of practicality is that X lives in X star. It lives basically, yeah, it kind of just, it sits in X star as a matter of practicality. You can kind of think of X as a subspace of X star. Okay, yeah, and the proof is pretty straightforward. Well, the fact that this is linear, there's really not much to that. I'll still do it anyway, just make sure we're all on the same page here. So let's say alpha and beta are scalars, X and Y are in big X. By definition, this is just going to be, well, the class generated by this constant sequence. Obviously, I should mention constant sequences are Cauchy. There's nothing to prove there. Well, by definition, this is how we add these two classes, or add these two elements in X star together. So this is going to be alpha phi of X, beta phi of Y. Now I should mention, if you've seen this in topology, this is the same completion as the completion of a metric space. Right? Okay. Right. So, right. So let's just look at what this is. Well, by definition, this is the limit. Right. So let's go back to the definition here. What's the definition of a norm of anything in X star? Well, you take the limit of the sequence here. Okay. Well, that's pretty silly. and there's really nothing here, this just gives me the norm of x because, well, this literally is just a constant sequence generated by x. So, right, so remember the definition is when we have a class like this, we literally just take the limit of xn, where usually we have xn here. I guess we still do, but xn is x for each x. So we stick it in here. Well, we just get, again, we get xn, which is x for each n. So no need to write n. It's just a constant sequence. So basically, by definition, there's really not much to do. This is isometric. Okay. Right. So this is all nice and dandy, but how do we know that this is complete? Well, let's prove that. And this is actually, it's so easy that if I gave a homework, you would probably instinctually try something much harder than the actual proof. Even when I try to prove this off the top of my head, I always forget that the proof is so easy. Okay, let's just do this by the books. Let's just, let's just write down a Cauchy sequence. So I'll use script X L for Cauchy sequence. So let's say, I don't want to write brackets like twiddles here because then I have to write twiddles here. But okay. So for each L, we have an element in my, well, let me just call it the completion. It's maybe inappropriate to call it the completion before we prove it's complete, but instead of calling it X star, let's just call this the completion. Okay. Yeah, let's say I have a Cauchy sequence in my completion. So what does that mean by definition? Then for any epsilon bigger than 0, there exists so let's use capital K instead of capital N. So for K and L bigger or equal to capital K, we have the following, and I'm going to leave some space here for a reason. Well, just literally write down the definition of Cauchy sequence is the following. This here implies that this is less than epsilon. That's just a generic definition, regardless of what norm, what norm vector space you're talking about. Well, remember what by definition this is. This is by definition the following limit. I hope I have room. I think I should. So it's xn L minus x n k. Okay. So by definition, this here is, well, what's inside the norm is the class generated by the Cauchy sequence xln minus xkn. So by definition, this is what the norm is, and this is in X. Okay. So we have an obvious candidate for what script XL should converge to. Let's just look at the diagonal. xn. And we're lucky that this diagonal works. It's pretty remarkable that this, constructing this is so simple, but anyway. Right, so let's prove that, in fact, we have convergence to XL. Okay, so for L bigger or equal to K, we have the following. This is going to be, by definition, this limit here. And yeah, I should mention you can prove very easily that this is actually a Cauchy sequence in big X. Not much to that. Right, so this is going to be script ln minus, well, by definition, n. And this is less than or equal to epsilon, well, actually less than epsilon, for the obvious reason that, well, I mean, both of these are, for large enough n, we're taking the limit. So we can assume n is bigger or equal to k. Yeah. Okay, so that proves it. This XL in X star converges to X script XL. The sequence in X star converges to this element X script X in X star. And again, proving this is Cauchy is a very, very easy homework. Really just have to use this here. Not much to it. Okay, so right. All right, so I want to investigate a little further this completion here, and I want to prove that essentially the completion is unique in the sense that well, I'll describe in what sense in a moment. So let me just prove some more very useful properties about this completion. As I said, this X star here, the completion is really not much bigger than X itself. So first of all, I claim, well, I'm going to prove what I said is true before, that essentially X is dense in X star. More precisely, phi of X is a dense subspace of X star, where again, remember what phi is. Phi just maps X to the constant, the class generated by the constant sequence X. Okay. And this makes sense. I mean, it's kind of what should be true, just like when you complete the rationals to get the reals, you should have, or what is true is that the rationals is dense in the reals. And all we're saying here is that this is generically true. And the proof, again, is surprisingly simple. Yeah, so I'll prove this. Thinking of making this homework, but I'll just prove it. Okay, right, so let's say epsilon is bigger than 0. Let's pick something in X star. So let's call it x hat. Okay, so this is a Cauchy sequence in X. So pick n where, well, usual Cauchy sequence definition. So this implies that xn minus xm is less than epsilon in X. Okay, so, right, so let's say, let's just pick little x to be xn, x big N. So I'm not, there's no sequence here. X big N is fixed. So this is a perfectly fine element of X, big X. All right, well, I claim that phi of X minus x hat is less than epsilon in norm. Okay. Well, what's this? Well, before I write the definition, phi of X is just this sequence here, and just to make sure there's no confusion, this is a constant sequence. This is, big N is fixed. Right? Or maybe I'll just, I'll leave it at that. All right, so what's x hat? Probably see where this is going. Okay, well, what is this? And again, this is a constant. Well, I mean, maybe that doesn't make sense. So I want to emphasize here that N is fixed. All right, so now let's go to the definition of what this norm is. Sorry, there should be a bracket here that matters all that much, but right, and sorry, there should be brackets here. So by definition, this is going to be the norm of xn, big N, minus x, little n. Well, this is less than epsilon, because without loss of generality, we can assume little n is bigger or equal to big N. Big N is bigger or equal to big N. Big N is big N. So both are bigger or equal to big N, again, because n is going, little n is going to infinity. And so just from this here, this is less than epsilon. Okay, right. And x hat was an arbitrary element in x star. So that proves it. So again, it's a really, really easy proof. Okay, so an easy corollary that's homework is the following. So I apologize, this is going to be a slightly long video, but yeah, it's just going to end up being kind of a long video, but I think it's better to put everything into one video than break it up. So a corollary is if x is complete, this is not that hard to prove. It's actually very easy to prove. Then we have that this map here is actually surjective. So in other words, this is actually a isomorphic, is an isometric isomorphism. Okay, so we have two normed vector spaces that are isomorphic as algebraic objects, as vector spaces, and they basically, the norms are virtually the same in that we have this function, this norm preserving function here, that's an isomorphism. So, yeah, just to summarize, phi is isometric isomorphism from X to X star or in other words, in a research paper or whatever, people would just say X equals X star, because as a matter of practicality, they're the same normed vector space. Right. They're just, in just the mathematical sense, they're basically the same object because they're isometrically isomorphic to each other. And again, isomorphism in the sense of a vector space.